Thank you for the introduction. So, my name is Haruki Sanada from NTT-based research laboratories. First of all, I'd like to thank the organizers for giving me the opportunity to present our work at such a nice workshop. And research work I will be talking today has been done in collaboration with Tohoku University in Sendai, Japan, and Paul Drude Institute in Berlin. And her work was partly supported by JSPS Kakenhi. And the topic of my talk is acoustic transfer and manipulation of electron spins. And as you know, electron spins are one of the candidates for future spin quantum information technologies. And also for this transport of electron spins is also important for investigating spin-orbit interaction. And the spin-orbit interaction is also important for the spintronics application. So this is outlining my talk. After the brief introduction, I will start with the how spin-orbit interaction in gallium arsenide acting on the electron spin transport. So, and we need electron spin transport, and so I will be comparing the how to spin electric field spin transport and the acoustic spin transport. And actually, how we are doing the experiment using the surface acoustic wave, and this enables us to modulate the band gap, and we can make a wire-like potential modulation or dot-like potential modulation, and this enables to observe the spin precession that depends on the moving direction. So, and I also introduced our measurement technique using the optical spin injection and optical spin detection. And especially the magnetic optical effect is very powerful technique to observe the two-dimensional image of the electron spin distribution. And in the last part of my talk, I will introduce our work on the spin manipulation using magnetic field-free electron spin resonance. This enables us to manipulate spin in arbitrary direction in three-dimensional shape, three-dimensional space. So this is a very important technique for the future spin quantum information processes. Okay, so now I'd like to start with a brief introduction. As I mentioned in the beginning, so quantum information processing using spins in semiconductors will require spin manipulation and also spin transport. And the important point is we want to do this without spin decoherence. And the key physical phenomena is spin-orbit interaction. This is because spin-orbit interaction induces effective magnetic field for moving spins. So this means we can process electron spin even the absence of external magnetic field. But it also has the adverse effect. This is fluctuations in the effective magnetic field induces undesirable spin decoherence, which limits the spin transport length. So it is important to understand the physics of spin-orbit interaction, and we want to control this. So we are interested in the spin-orbit interaction in gallium arsenide, and the gallium arsenide has the zinc-brane crystal structures, and because of this symmetry, or because this crystal doesn't have the inversion symmetry, this leads the spin splitting in conduction band. This spin splitting is expressed by this formula, which is proportional to the material constant gamma and cubic term of the momentum vectors, K is momentum vectors, and Pauli matrices. Because it contains Pauli matrices, it is, can be understood as the effective magnetic field. When we use the two-dimensional electron system, we can simplify this formula to here. So in this formula, we only have the K linear term. So we can write the effective magnetic field that depends on the momentum component like this. So it is also known that there is another type of spin-orbit interaction called Rashba spin-orbit interaction. In this spin-orbit interaction, inversion asymmetry is induced by externally applied electric field. And the Hamiltonian can be written in the same form of the Dresselhaus spin-orbit interaction, except for the coefficient alpha, which is proportional to electric field, and also the component and the sign of the momentum vectors are slightly different. And we also have the strain. We also have the strain-induced spin-orbit interaction, but it also has a similar form of the Dresselhaus and Rashba spin-orbit interaction. So we can write the effective magnetic field in a momentum space like this. So the Rashba spin-orbit interaction is simpler than the Dresselhaus one because the effective magnetic field is always perpendicular to the moving direction. Now, on the other hand, the Dresselhaus spin-orbit interaction has a little bit more complicated direction dependence, but we can calculate with this simple formula. In actual material, these two spin-orbit interactions coexist. That means we can. The amplitude and the angle of the effective magnetic field depend on moving direction. In other words, if we can measure this dependence on the moving direction, we can access to the origin of spin-orbit interaction. So it is important to measure the moving direction dependence of spin transport. So how to transport the electron spin? So the most straightforward way of transporting electron spin is using the electric field, because the electron spin, of course, electron spin has the negative charge. And in the first stage of the spintronic studies, they used the electric field to transport electron spins. And they discovered the electron spin can be transferred for macroscopic distance from the microns to the 100 microns. And after, they were using the bulk gallium arsenide, and because of that, because the spin-orbit interaction in bulk gallium arsenide is not so strong, so they did not observe the effect of spin-orbit interaction. But when we use the two-dimensional electron system made of the gallium arsenide system, so we can observe the spin precession. So this is a spin precession induced by the strain induced by spin-orbit interaction in the absence of external magnetic field. And we are also interested in the spin transport experiment using the electric field. So recently, we have shown that the robust spin structure called persistent spin helix condition can be transported by electric field. So we don't have enough time to explain this in detail, but when we transport the spins along the one direction, the electron spin does not precess. But when we transport in the orthogonal direction, we can observe the spin precession. This is a strong evidence that we can achieve the persistent spin helix condition. And this is another way of the spin transport using the surface acoustic wave. This is the first experiment we have done in NTT. So we use the acoustic wave, we use the gallium arsenide quantum error structure and applied acoustic wave, and we observe the electron spins can be transported by the acoustic wave. So in this experiment, the suppression of electron-hole exchange interaction is very important to extend the spin lifetime or spin and transport length. And in Paro's group have shown that the spin-orbit-induced spin precession can be observed even in the moving quantum dots. And later, so Paro's group, PDI's group, and our groups also show that Kerr imaging technique can be probe the spin distribution in quantum well structures. So, and also we are clarified that there is acoustically induced spin-orbit interaction. So I will be talking about this experiment and this experiment later. So now I can summarize the difference between the electric field transport and acoustic transport of electron spins. So I didn't mention about the doping, but for the electric field transport, basically we need the conducting channel. So that means we need the doping. But we have to be very careful about this because the spin lifetime depends on the carrier densities. So we have to choose the appropriate doping densities. But for the acoustic wave transport, so we do not need doping. In general, the spin lifetime, electron spin lifetime in undoped sample is quite slow, quite fast, but we can extend this because of the electron hole separation. I will come back to this later. And for the velocity, so we can velocity can be very fast for the electric field if we use the high mobility sample, and also the velocity can be changed by changing the bias voltage. But for the acoustic wave, it is constant constant, and it is same as the acoustic velocity. And as far as we are using the two-dimensional electron system, we cannot neglect the spin diffusion. So for this, because of this, it is the transporting electron spin packets from one position to another position. This diffusion, because of this diffusion, the efficiency of the transport is not very high. But by using acoustic wave, we can suppress this effect if we use the dynamic dot spin transport. And also for moving direction dependence, we can measure this by choosing the configuration of an ohmic contact in the electric field spin transport. And but for the acoustic waves, so when we form the certain IDTs, we cannot change the propagation direction. But I will show how we can control the direction by using a special technique. Okay, so now I'd like to focus on the acoustic wave spin transport. So as you know, the acoustic wave can propagate along the surface of elastic body. And in semiconductor, this induces local strains that modulate the energy band structures. So then the strain is generally expressed by the tensor, and this can be classified two terms. One is hydrostatic strain, and the other is shear strain. Hydrostatic strain changes the lattice constants, thus it changes the band gap energies. And for shear strain, this changes the lattice shape, and this induces the piezoelectric field. And in the case of the acoustic wave, so this induces the local or spatially and time-dependent local strain. So this local strain induces the local band gap modulation and the local piezoelectric field modulation. So because so the difference is for the type 1 band gap modulation has the type 1 modulation, and piezoelectric field modulation has the type 2 modulation. Type 1 and type 2 mean the phase of the modulation between conduction band and the valence band is out of phase or in phase. And we can, because the strength of the piezoelectric field modulation is much larger than the band gap modulation, we can use this piezoelectric field modulation for transporting electron spin. So when we create electron hole in this some conduction and valence band, they are trapped in their potential minima and transported with the acoustic velocity. This is a typical sample structure that we are making. So we use the gallium arsenide, aluminum gallium arsenide quantum error, single quantum error, and on top of the sample, we form the interdigital transducers. We usually use the double finger type transducers to suppress the acoustic reflection. So and when we apply the high frequency voltage, the acoustic wave propagate along the 1-by-1 direction in this configuration. And to confirm the electron hole pairs are transported, we can use the photoluminescence. So we can excite at some point here and generate the electron hole pairs. And these electron hole pairs separated by the external piezoelectric field. And they are transported in this direction. And at this region, we form the semi-transparent metal. This metal partially screens the piezoelectric field, and it increases the probability to the chance to recombine the electrons in the hole pairs, and we can detect the photoluminescence. So this is data. Here, vertical axis is PL intensity, and horizontal axis is distance between excitation position and the detection position. And without acoustic wave, we can observe the photoluminescence at the position close to the excitation position. But when we increase the acoustic wave intensity, we observe the photoluminescence here, even at the distance longer than the several microns. So we increase the intensity, we observe higher PL intensity. So this is evidence that we can transport the electron hole pairs. Then what we have to do to measure the electron spins? This is very simple. We can excite these electron spins by using circular polarized light. And what we have to do for the detection is we measure the polarization, circular polarization of luminescence. So this is based on the selection rule of the optical transition. It is known that electron has this spin 1/2, and the heavy hole and the light hole has 3/2 and 1/2 of the angular momentum. And when we tune the laser energy to between the heavy hole and the light hole, and we change the polarization to the right circular polarized light, we can excite only spin -1/2 electrons. Or when we excite sigma minus polarization, we can excite spin 1/2 electrons. And in other words, the circular polarized light carries angular momentum. And the opposite case is for the spin detection. And the spin states can be detected by polarization-dependent optical responses, such as luminescence or magnet optic effect. So, and I didn't mention about the Hall spin, but it is known that Hall spin has a rapid spin relaxation time, so we can observe only the spin of the electron. So this is a polarization versus the distance between excitation and the detection position. And they observe the spin precession like this. Oscillation means the spin is precessing around some magnetic field, but they didn't apply magnetic field, so this is due to the spin-orbit interaction. So again, the long spin relaxation time is induced the long transport length, and this spin precession is induced by spin-orbit interaction. But this method also has a disadvantage that because we have to determine the metal position of the metal at first, so we cannot scan the detection position. And also, there is electron-hole exchange interaction just before the emission of the photons. So this decreases the polarization of the electron spin. So we think this decreases the signal-to-noise ratio of the measurement. So this is why we want to measure with the magnet optical effect. So I'd like to show you our data. So we use the gallium arsenide, aluminum gallium arsenide single quantum structure with a thickness of 20 nanometers. And at the top of the sample, we formed the two interdigital transducers made of 50 nanometer thick aluminum. This is the wavelength. And when we apply the signal, 1 gigahertz signal to the IDTs, we can propagate the acoustic wave to the 1-by-1 direction, which produce the wire-like potential with a velocity of 2.9 kilometers per second. And if we apply the signal to the this IDTs, this produce the acoustic wave along the 1-by-1 direction. And when we want to transport the electron along the O1 direction, we can produce the dot-like potential by using the interference of two orthogonal acoustic waves. So in this case, the speed of the dot is square root of 2 times the acoustic velocity. Okay, and this is how to detect the magnet optical effect. So we use the CW type sapphire laser, or sometimes we use the pulsed lasers and delay lines for measuring the pump and probe method. So and this is a photoelastic modulator which modulates the polarization pump beam between right circular polarization and left circular polarization. And this polarization excited spin spin polarized electron at a certain position of the sample. And we can detect the Z component of electron spin by using magnetic effect. We use the linear polarized light, and we measure the angle of the polarization of the reflected probe beam. This theta k is proportional to the Z component of electron spins. So if we can scan this probe position, we can measure the two-dimensional images of the electron spin distribution. So this is the real image of our sample, our setup. So this is a cryostat, and the sample is in it. And the cryostat is on the XY stage. And on the same XY stage, how we prepare the pump beam excitation unit. So a pump beam is fixed to the same position of the sample. And probe beam comes from this objective range. So if we can we scan the XY stage, we can scan the only probe position. Okay. And this is some data we measured with the pulse laser. Here is the car rotation signal versus delay time. And at the this is the pump probe distance. So when the pump and probe beam overlapped, so we observe the spin signal at the delay time of the 0. But when we separate the pump and probe beam, we observe the signal appear at the some delayed time. So we can plot this in a color map as a function of pump probe distance and the delay time. And when we increase the acoustic power, we can observe the signal appear in this slope. So this slope determined by the acoustic velocities. And this oscillation is due to this spin-orbit interaction. And also, sometimes we observe this kind of modulation in the signal, but this phase does not propagate with the acoustic wave. This means this is probably due to the standing waves produced by the reflected acoustic waves at the edges. So we don't want to see this, but we want to see this oscillation to understand the spin-orbit interaction. So we can measure the same situation with the CW laser. So we excite the spin polarized electrons at here and transport them along the O1 direction with the moving dots. Please. But we also measure the spin transport with moving wires along this direction and this direction. And the large difference is for the moving wire, we observe the spin diffusion along the wire direction. But in spite of that, we can observe one period of the spin precession. This enables us to know to analyze the spin-orbit interaction. So we can overlap these data in one graph here. So as you can see, the ice phase line of the spin precession clearly have the elliptical shapes. This means the precession frequency depends on moving direction. So we can fit the data along this direction and this direction with a simple cosine and exponential decay function. And from this is a precession spatial frequency of the spin precession, and analyze these values the function of the acoustic intensities. So this is the this graph shows the precession frequency varies with the acoustic intensity, which means the acoustic there are some reason to modulate the spin-orbit interaction by using the surface acoustic waves. So by analyzing these data with the theory, we conclude that strain-induced spin-orbit interaction induced by surface acoustic wave can be tuned by adjusting acoustic intensity. Okay. So I put the same data I showed before, but if possible, we wanted to reduce the spin diffusion in this direction. So this is also possible like this. This is possible by using the this type of device. It's very simple. We put the metal film with slit. So this metal or slit stripes induce the electrical channels for acoustic transport. the reason is like this. So this titanium film, we use the titanium film, and this film screens a part of the piezoelectric field. That means the electrons feel the larger potential modulation than the here. So this switch shape determines the channel for electrons. So by using this, we are doing the new experiment. So, so far, we are measured the spin precession around the static magnetic field, effective magnetic field. This is the two-dimensional motion. So that means the motion is restricted in a two-dimensional plane. But when we can induce the electron spin resonance, we can change the direction of the spin in three-dimensional shape. So this is needed for the future spin qubit operation. So, so this is electron spin resonance has the diverse application. Of course, have the diverse application. And also, as I said, it has the potential for use in manipulating electron spin in future information technologies. And in technical aspect, the ESR requires two types of external magnetic field. One is a static magnetic field, B0, that splits the spin state in energy, and the other is oscillating magnetic field, B1, with a frequency resonant to the splitting energy. But usually, these externally applied magnetic fields are produced by the electromagnet or microwave cavities, and this generate the magnetic fields, and which extent is much larger than individual electrons. So, but we want to control this individual electron spin when we want to use the as the spin quantum information. So the device structure will be complicated and energetically inefficient for future spin information processing on a chip. So this is why we want the alternative way that does not require real magnetic field. So, so far there are several studies that have shown that reciprocating motion of electron can induce the effective oscillating magnetic field. For example, the electron G factor can be tuned by the external gate voltage. This enables us to access to the to produce the oscillating effective magnetic field. And also the movement of the wave function in the quantum dot can in a slanting magnetic field can induce the effective oscillating magnetic field. And other researcher is using the spin orbit effective oscillating magnetic field. But all of these experiments still need the assist of external static magnetic field. So we wanted to replace all the magnetic field with the spin orbit effective magnetic field. So the answer is now clear because we already know that effective static magnetic field acting on electrons moving with the constant velocity, as I have shown already. So we can use this. So to simplify the model, we assume the K-linear terms of Dresselhaus spin orbit interaction in O1 plane of 3-5 semiconductors. So we can plot again the effective magnetic field, and we consider the electrons moving along winding channel like this. So for this electron, this electron has the momentum vectors that oscillate like this. And corresponding effective magnetic field expressed by red arrows here also oscillate with a frequency determined by the velocity along y direction and wavelength of the winding channel. So this oscillating magnetic field can be expressed by the static magnetic field and oscillating magnetic field. So if this spin orbit effective magnetic field meets the resonance condition, we can expect to drive the coherent Rabi rotation. So what we did is like this. So we formed the switch, metal fin with a switch with the form of like this. So we prepared a straight channel and winding channel with slit width of 3 microns, and we choose the wavelength of 23 microns and amplitude of about 4 microns. So these parameters are designed to meet the ESR condition. So this is a very simple mathematical representation of the transport path. So we can model this with the amplitude and the wavelength and the initial phase of the channel. And the electron velocity along these directions are determined by the acoustic velocity. So Vy is acoustic velocity. And for Vx direction is determined by these parameters and oscillate with time. And this static velocity induces the static effective magnetic field along this direction. And this oscillating magnetic field along x-axis induces the oscillating magnetic field along the y direction. So we measure the spin dynamics with the same setup I have shown already. And this is the data. So we excited spin polarized electrons at this position and transport them along this direction. So we see the signal oscillate with the, some frequencies, and also we observe the signal even at the 100 microns. So this data shows the successive carrier transport along the straight channel. And for the winding, so actually, so random fluctuation of the oscillating magnetic field is known to cause the diagonal parallel spin relaxation. But the motional narrowing by the mesoscopic confinement due to the surface acoustic wave elongates the spin lifetime. And as a result, electrons feel the effective magnetic field determined by this acoustic velocity. So average field can be expected to be proportional to the sound velocity. And for the winding channel, we also observed the similar oscillating behavior. But when we focused at this region, we noticed that the spin precession phase inverts. So here we start the spin up, here, down, up. But when they come to here, here is up, but here is down, down, up, down, like this. So this phase inversion is due to the Rabi rotation of the electron spin resonance. So, so we can simulate this phenomenon by using the by solving the Bloch equation. So this is the spin dynamics along the spin dynamics of the electron moving along the straight channel, and this is the winding channel. And the Kerr rotation data can measure the Z component electron spin. So we want to focus on the Z component electron spin. So now Z component is out of phase. Here is down, up, up, down, down, up. And at this point, they are in phase, down, down, up, up, down, down. Again, here is in phase. But when this spin comes to the x direction, they invert. So up, down, down, up, up, down. And they come to this direction, they recover again, down, down, up, up, like this. So now we can understand why the precession phase inverts when, in this region. So next, how we for the quantitative discussion, we apply the external magnetic field. So we apply the external magnetic field along the x-axis. This is the direction of the static effective magnetic field. So here is the Kerr rotation signal as a function of the y direction and the external magnetic field. When the external magnetic field approaches to 23 meters, so the spin precession slots almost halt at this position. This means the external magnetic field of 23 meters cancel out the spin orbit static magnetic field. So and we can plot the precession frequency as a function of external magnetic field. And from the slope of this plot, we can determine the G factor of the this system is 0.36. And by using these parameters, we can reproduce this behavior like this. So from this data, we can show the spin orbit static magnetic field acts on the spins in the same way as the external magnetic field along the x-axis. For the winding channel, we also apply the magnetic field in the same direction, and we see this characteristic features around here and here. So this is caused by the electron spin resonance. So the reason why these appear in two regions is like this, because the spin dynamics is determined by total magnetic field. For here, the external magnetic field is 0, so the total field is determined only by the static spin effective magnetic field. So for here, the external magnetic field is 46 millitesla, but the total magnetic field, this effective magnetic field is 23 millitesla, so 46 minus 23 millitesla is 23 millitesla. So the resonance occurs when the total magnetic field is 23 millitesla. So we also calculate the spin dynamics using the Brough equation, and we incorporated the spin orbit effective magnetic field here. And this shows the quite good agreement with the experimental data. And the important point is we can achieve the resonance even at the 0 magnetic field. So we can we can achieve the magnetic field free electron spin resonance by using spin orbit interaction. Okay. And next we measure the phase dependence. So initial phase means initial phase of the oscillating magnetic field. We can change the initial phase of the effective magnetic field by changing the pump position. Like so we define the initial phase phi like this. Here it's phi equals 0. When we excite here, it's pi half, and so on. So so this affects the spin dynamics Mach 3. So here is the phase, and here is the y direction, and it depends on the this dynamics depends on the initial phase. So this is also reproduced by the Brough equation, and this is very complicated, but I try to explain that. So here we can find the whitish region. This means the Z component electron spins doesn't have the electron spin doesn't have the Z component. This means the electron spins are in x, y plane. So this means the electron spin comes to around minus x direction or plus x direction and come back again. So for this condition, the ESR occur efficiently. However, in this condition, so the period of the oscillation is always the same. So this means that it's like the normal spin precession. So the rapid rotation occurs inefficiently. Okay, so from all of these experiments, we can say that we can prepare any spin direction by controlling the phase and amplitude and the transport length. Finally, I'd like to mention about the effect of the Rashba spin orbit interaction. So here is the period of the rapid rotation, which was found to be 180 microns. This value was slightly longer than the expected value of the 93 microns. And we consider this is due to the Rashba spin orbit interaction. So before now, we neglected alpha, Rashba coefficient alpha. But if we incorporate this in the effective magnetic field, this can be written like this. And this x component of the effective magnetic field induces the static magnetic field, and y component induces the oscillating magnetic field. And this depends on the alpha over beta. So we plot the B1SO as a function of alpha over beta, and this shows the that alpha reduces B1SO. So we see the here is the 0.13. So that means the this system has the Rashba spin orbit interaction, which is about the 1 order of magnitude smaller than the Dresselhaus spin orbit interaction. We consider this alpha-type spin orbit interaction is induced by the unintentional strain or acoustically induced spin orbit interaction, as I explained before. Okay. In summary, we have studied the acoustic spin transport for spin-based quantum information technology, and also for investigating physics of spin-orbit interaction as well. And moving direction dependence of the spin precision enable us to clarify the acoustically induced spin-orbit interaction. And by designing the transport channel, we can demonstrate magnetic field-free electron spin resonance. This is an important step toward spin-orbit operation, spin-qubit operations. So this is the final slide. I'd like to thank our collaborators in NTT. He is the director of the NTT Basic Research Laboratories, and this is the group leader of our group. And he measured the optical, he done the optical measurement with me, and he made the sample by molecular beam epitaxy. And Makoto Koda and Junsek Nitta, he is a professor in the Tohoku University, providing us the great support about the spin-orbit interaction. And of course, Paulo Santos have the very nice advice about the surface acoustic waves. And Kenichi Sasaki is a theorist and give advice about the spin-orbit theory. Okay, thank you for your attention.
Thank you very much
Yep.
for this nice presentation. So I'm sure there were lots of questions.
So, thanks for the nice talk.
Thank you.
The ESR measurements with external fields, in the measured data, the oscillations, spin oscillations decayed at magnetic fields beyond 60 millitesla or so.
Mm-hmm.
Why is that the case?
So, do you mean this data or?
Go a little bit back. Yeah, here.
Yep.
You see the calculated data do not decay.
Yep.
60 millitesla.
Yep.
The measured data decay.
Yeah, this is a simple. This has a simple reason because our setup have the resolution of the determined by the spot of the laser. So this means we cannot resolve the very fast oscillation in length scale. So we cannot see the some data. And also,
oscillation speed doesn't change so much anymore. If you look at the lower plot, it's almost horizontal.
Here.
At the lower left corner, suddenly it seems that at minus 50 millitesla, the lines just end. So on the right side, at minus 45
and
you can see it, at minus 6 you don't see it, but the oscillation frequency is almost the same.
You are mentioning about the decay length, or so actually we didn't discuss about the decay length about this measurement. So maybe we can discuss later about this, but it is not easy to access to the spin relaxation mechanism in detail by using this technique. So,
okay.
Other questions, please?
Yeah, in this, you're using external magnetic field. Did you see any attenuation of the soul at the external magnetic field?
Not so much, I think, that affect the
So
data.
have you tried higher magnetic field? No.
No, we could not apply the higher magnetic field.
Maybe start here.
Again, a question regarding ESR. So one of the major achievements of ESR is measuring coherence times with schemes like Hahn electrospectroscopy.
Yep.
And you encoded your pulse, so to say, in this trajectory of the motion of your electron.
Yep.
Is there any trajectory which would allow you to do Hahn electrospectroscopy?
Yes. So to do that, we need to prepare the complicated channel structures. Maybe that can be that will allow us to measure the some spin echo spectrum. But also we are doing the spin transport with the electric field, and we can see the some movement of the trajectory by using the oscillating electric field. So this is very useful to change to choose the trajectory of the electrons freely.
Yes.
So these experiments are made with an ensemble of spins.
Yes.
So do you think you can go down to the single spin level?
Yes. So we want to do that, but so to do that, we need to make the size of the dot smaller, and so this means in this experiment we have the a lot of electrons, maybe from 100 to 1,000 in one moving dot. But we can reduce by reducing the optical excitation power. But at the same time, we reduced the signal to noise ratio. But instead of that, when we can reduce the size of quantum dots, we can make a lot of quantum dots at the same time, and we can measure the ensemble of the dots. So this is one strategy that we are thinking now.
But technically, you could measure a single spin with optical?
Yes, the UCSB group have measured the single spin in a quantum dot. So I think it is technically possible.
Maybe it's your second. Yes.
When you had the crossing beams,
Yep.
you showed the spin relaxation in different directions and the power dependence of that. Sort of somewhere in the middle of the talk.
Yes. Here.
Yes.
Here.
So I mean, there's a very weak power dependence, but it seems to be different in different directions.
Yes.
So-
So this is very complicated. This is the moving dots, and this is the data for the moving wires. So
Yeah.
that means 40 degrees different from the moving dot.
So why is the power dependence different in different?
Yes, we analyze. This is a little bit complicated to explain, but so we can analyze the data with the acoustically induced strain in a minimum of the potential modulation, and then this have the hint to access the this dependence on the acoustic intensity. And actually, the theory says that this increases and here decreases and here increases. So we are not sure why this cannot explain by the theory.
So can you calibrate the SAW amplitude?
Yes, because I said how we can neglect the effect of strain, but there is an effect of strain that changes the hydrostatic strain that changes the band gap energies. So from the photoluminescence energies, we can estimate how strong the acoustic intensity is.
Maybe, if I remember correctly, if you have the dots, the hydrostatic strain is 0 at the points where you confine the electrons in the dots, because you just have the piezoelectric potential. So there is a phase difference between the strain dots and the piezoelectric dots. And where you have the piezoelectric dots, you don't have hydrostatic strain.
In the dots?
In the dots, yes. Okay. And maybe this is one of the reasons why you actually have such a...
Maybe. Thank you.
Additional questions? Fathers?
I wanted to ask about the winding.
Yep.
Winding path.
Yep.
Could you show the?
Here?
No, the design.
Okay.
The winding channel you used to titanium fume.
Here?
That
Yep.
one. So for the straight one, the soul, it wouldn't be attenuate along the path, but for the winding one, when the soul propagate alone, you will always see some metal in the past. Then that attenuate the soul power more.
I see. Probably there was some extent of the acoustic wave attenuated by the here, but we did not see the effect is significant.
So basically,
we can analyze the data with the acoustic wave is not attenuated by the this film. Acoustic wave is not affected by this here, but the piezoelectric field that experienced by the electron is modulated by this structure.
So additional questions?
Do you think it would be possible to get such a meandering trajectory also by interfering surface acoustic waves and changing the?
Yeah, that's a good idea. So I'd like to try. So you mean the creating the channel that combine, combine and see the interference effect or something. Yeah, that's interesting. We want to do that.
I guess there was actually a proposal to make the two beams, to change the phase of the two beams and have some kind of beams that actually circulates. I think Tetsumi Sogawa had some ideas around that direction.